4 light-years away, orbiting the closest sun-like star to Earth, astronomers detected something that looked exactly like a hidden planet. And then it vanished. That star system is Alpha Centauri. At just 4.37 light-years away, it is our cosmic next-door neighbor. If humanity ever launches an interstellar mission, this is the most realistic first stop. We routinely spot exoplanets hundreds or even thousands of light-years across the Milky Way. We have confirmed thousands of them, but trying to find one right next door, it has been almost impossible. Being close does not mean being visible. Alpha Centauri breaks almost every rule astronomers rely on when hunting for exoplanets, turning our closest stellar neighbor into a highly complex investigative challenge. The first hurdle is sheer brightness. Alpha Centauri is the third brightest stellar system in our night sky. Trying to image a faint planet next to it is like trying to photograph a firefly hovering right beside a stadium floodlight. The glare completely swallows the signal. To make matters worse, it is a binary system. Two distinct sun-like stars orbit each other, flooding telescopes with scattered light. Traditional coronagraphs, the physical masks inside telescopes designed to block starlight, struggle badly in this chaotic environment. These stars also move rapidly across our field of view. That constant, fast motion makes extremely precise, long-exposure tracking incredibly difficult to maintain. And because Alpha Centauri sits near the dense, crowded plane of the Milky Way, the background is packed with distant stars and galaxies. Any faint blip you detect might just be unrelated light coming from billions of miles further away. Extreme glare, rapid motion, and a deeply cluttered background combine to form an impenetrable shield. That is why, for decades, this system remained an absolute cold case. Enter the James Webb Space Telescope. Webb was never designed to look at nearby blazing stars. Its massive, highly sensitive mirrors were engineered to capture the faintest light from the edge of the observable universe. Aiming instruments this sensitive directly at a target as bright as Alpha Centauri poses a serious physical risk to the telescope's hardware. So researchers tried a different approach. Instead of looking for reflected visible light, they used Webb's mid-infrared instrument, or MIRI, to hunt for the faint thermal glow, the actual heat radiating from a potential planet. To do this safely, they had to invent a workaround called blind offsetting. First, Webb locks on to a safe, dimmer reference star. Then, using exact mathematical calculations, it shifts its aim slightly off-center from Alpha Centauri, observing the space around the star without staring directly into the glare. This requires terrifying precision. An alignment error smaller than the width of a human hair, viewed from kilometers away, ruins the observation. In fact, the very first attempt in 2023 failed completely, yielding unusable data. The eventual success of the 2024 observation represented a high-wire technological hack of our most complex space observatory. Even then, the raw data that came back looked like absolute chaos. The images were completely flooded with massive diffraction spikes, instrument noise, and scattered light bleeding in from the binary companion star. Astronomers had to treat the image like a forensic crime scene. They processed the data layer by layer, mathematically subtracting known optical artifacts and carefully filtering out the remaining background static. Once the glare was cleared, a tiny infrared blip appeared roughly 1.5 arcseconds away from the main star. The team labeled this faint anomaly S1. Immediately, they tried to rule it out. Was it a background galaxy? No. A check of deep space catalogs showed nothing matching those coordinates. Could it be an asteroid? The object did not move during the observation period, and extensive testing confirmed the signal survived multiple, highly varied processing methods, making a simple software glitch unlikely. S1 survived all immediate scrutiny. For a brief moment, the scientific community had to confront a startling possibility. They might be looking directly at an undiscovered world, sitting right next door. But then the investigation hit a wall. When researchers conducted follow-up observations to confirm the object, they completely failed to recover it. S1 was gone. This vanishing act immediately split astronomers. Skeptics argue that S1 was likely a highly complex optical illusion, a deeply buried instrument artifact that somehow slipped through Webb's initial filters. Others suggest a physical explanation. If S1 is a real planet, its natural orbital motion over the course of the year might have simply carried it out of view,
burying it directly beneath the star's blinding, unfilterable glare. With the signal lost, the trail went cold. We are left with fiercely competing theories, divided experts, and absolutely no definitive proof in either direction. We often expect astronomy to deliver pristine images and clean, absolute answers, but the S1 anomaly reveals what real science at the very edge of human capability actually looks like. It is incomplete, frustrating, and heavily debated. The stakes in this debate are enormous. If this planet exists, it is close enough that future generations already have theoretical mission concepts capable of sending physical probes there within our lifetimes. Astronomers are not giving up. They are currently preparing entirely new observation campaigns, waiting to see if S1 emerges from the glare once again. By pushing its hardware past the point of intended use, Webb revealed that the closest stellar system in the galaxy is still keeping profound secrets in the dark.